Cedric invited me to say a few words on my activity. So I spent most of my life in France at INRIA. I spent about 10 years in the US at UT Austin. And I'm currently working on an ERC project on the use of stochastic geometry for various types of problems, and in particular wireless. So in a few words, I have lots of interaction. Yeah, which is also certainly one of the reasons for which Cedric kindly invited me. I had fantastic colleagues and students. I have fantastic of India, both in the US and here, both in EE and CS and math. And you must know, for instance, for start with math, Yogeshwaran Dandapani with the Indian Circle of Science in Bangalore. I had also quite good interaction. They were not my students, but as postdoc with Anu Biswas, who is also a mathematician more on the control side, and with Radhakrishna Ganti, you must know him. And one of the papers I will describe here, which is already a known paper with him when he was a postdoc at UT. Okay, very good. So, and I'm very often in India and quite willing to develop more interactions. Lots of names. Abhishek Chatterjee, you must know him perhaps. He's also in Madras now. Very, very strong scientist and amazing people. I would like to add one name, which is a very, very, very nice person. I know he's not in India anymore. He's now working with Amazon. His name is Abhishek Sankararaman, quite amazing fellow. I could have like another half dozens of people for whom I have the highest admiration. So, okay, we have in postdoc and also very strong colleagues here, Abhishek Sankararaman. And so, okay, anyway, so very strong interactions, and I hope to continue and to develop more. Okay, so what I decided to do today is to survey what stochastic geometry is all about for wireless networks. So because I was not sure everybody would be familiar with that, and then to focus on 2 or 3 topics which are the core of this workshop is all about, namely topics that stem from 6G and for which we started developing with various co-authors the stochastic geometry vision of these problems. So one of them will be RIS, the other one will be NTN, and the final zoom will be on the interplay between RIS and non-terrestrial networks. Okay, so let me start with what stochastic geometry is all about. And so it might be superfluous for some of you, but perhaps not for all. So you represent basic objects of a network as special point processes or special random structure, random closed sets, whatever. And you represent, so for instance, base stations, RIS, things like that, right? Or non-terrestrial objects, I mean, UAVs and so on. And you represent interference as a functional of these point processes, as what is called the short noise process. So I will explain what these things are, but you see showing up already the 2 ingredients. I mean, if you treat interference as noise, I will only discuss that as an information theoretic setting. You have a representation of what in information theory would have, I don't know, the gain matrix or something like that. And geometry is not, in a sense, absent. You have one geometry. With stochastic geometry, you average out over all geometries and are able to make statistics. And there is notion of typicality that we'll explain a bit later. You can also introduce concepts which are very central, like connect to the closest. This will be linked to what are called the Voronoi tessellations. And then you get a framework where you can represent, I mean, the association to the closest base station and treating interference from the other base station as noise. You already see that you have the ingredients at hand. The short noise on one side, the Voronoi structure to get with the closest, and the power of signal. And so you can already devise what can be. So it's a very old thing. It was started by Kolmogorov for material science. There is an excellent book by initially Stoyan, Kendall, and Mecker, but there is a new edition which cites and has a full section and chapter on wireless and the type of models that can be developed for that, right? So it's recognized now that that stochastic geometry has a wireless branch, and beyond the material science, cosmology, epidemiology, and things like that. And for the more recent thing, you can check a book online that we have with Bartek Vlasichin and Mohamed Karai, which is where you will also find the Mass Foundation. The wireless part started around year 2000. So I will describe today only what in the context of cellular, but it has lots of incarnations to Wi-Fi networks, self-organized networks, IoT, and we'll describe NTN, right? So, I mean, what I will only discuss cellular, but more can be. And so it was non-existent, say 15 years ago. And now just Google the three words without quotes, wireless stochastic geometry, you get millions of hits. So it's an interesting thing of, it is in a sense, fact that now this thing is recognized as one of the approaches to assess the properties of large cellular networks worldwide. There are tons of books and papers and so on. Okay. So let me describe the paper with Radhakrishnan and Jeff, right? So because this will be variants on this. So it's so this is the Poisson-Voronoi tessellation, right? You see the points which are here, which would be like the base stations. You see the users, and users connect. These are fictitious links, right, to the closest base station. And you know it tessellates. I mean, the set of base stations tessellates the plane into these convex sets, which are called the Voronoi sets, which are they are convex because they are intersection of half spaces, right? I'm closer to this point than to any other point. Defines this type of set, right? UE is located according to some independent stationary point process, which doesn't matter, and each UE is served by the closest base station, which creates the Poisson-Voronoi tessellation. There is no information theory yet, right? Now you introduce information theory, and so again, I'm sure there are plenty of very strong information theorists in the room. We go way beyond treating interference as noise. The interference channel, the broadcast channel were assessed within these tools, but I will just describe a case where you treat interference as noise. Right? So the SINR is the signal over the interference plus the thermal noise. And so the signal power stems from the closest base station. And we will use the magic of Poisson and Voronoi to, they will interplay in a nice way to assess what this power is. The interference, as I said, is what stems from all base stations outside the Voronoi cell of the typical user. There's notion of typical user, which everything will be, these point processes will be stationary. And notion of typicality, you can think of it, so there is a typical locus, there is a typical base station, and there is a typical user. And what is a typical user? So, so think of a huge ball in the Euclidean plane, and pick one of those at random. From this point, that's what you see. Or if you make a big average of all users in that ball, that's what they will see. Local geometry. So that's typical. And so you then stipulate that the Shannon rate offered to the typical user will be the log proportional to the log of 1 plus SINR. And you want to assess what this fellow, this typical fellow, sees in terms of Shannon. Okay. And for instance, you can define the simplest question is the coverage probability. You get a threshold T, and you ask what is the chance that the SINR exceeds T, which is equivalent with change of function to that the Shannon rate exceeds a certain function, which is given here. And typicality is in terms of what are called palm probabilities, but it's not so important here. Define what mentally typicality means. Okay. And as I say, if you can assess, if you can give an expression for this probability of coverage at T of the typical user, as in statistical physics, this is equivalent to making spatial average. That's what I said. It is the average fraction of users who achieve a SINR at least T, or the average fraction of space where T in T coverage. Okay, so for the time being, we'll describe just the case where the attenuation function is R to 1 over R to the beta, right? The path loss, where beta is the path loss exponent. And I will take Rayleigh fate with an exponential fate with mean 1 over mu. So mu, to say mean 1, but you can say that the power of transmission. Average power transmission by base stations would be 1 over. Okay, so this is the setting. And with Radhakrishnan and Jeff, we got this explicit representation. I will say a few words on how to get it. But this is, let's draw a constant in this case, which depends on the t and beta. So the t at the power 2 over beta times this integral. Who cares? So just a function of t and beta. And then you see, so the beta would be 4. You would see a Gaussian type integral, right? You would have a closed form. If beta is different for the path loss, you take something different from 4. You get something which is a bit more integral, which is an integral form. Lambda is the intensity of base stations. Rho is this guy. Mu is the power. T is the threshold. Okay, you get a closed form expression or integral form for the chance to be closed. And we'll show the ingredients in a few words. But let me give the 3 steps. Step 1, you ask where is the closest guy, the closest base station. And there will be an empty ball condition, which I will describe. And thanks to Poissonianity, you can express this and as an exponential condition. Then you ask, given that the closest base station has distance r, what is the power of interference? When you want this ratio, right? Si and r, right? And you will assess, you will reduce that to thanks to special property of the Poisson point process to the short noise created by a Poisson point process outside a ball of radius r. Because there is nobody, is the closest, this ball of radius r. It's empty of fun. Interference is stems from the other way. Okay, and then you get the Poisson-Voronoi-Shannon formula, which will be this chance to be covered, or if you want, the CDF of the Shannon. Okay, so that's the story. Let me explain just a little bit how it works, right? So this is, because I will extend that a bit later, this is the chance to find the closest guy at distance r, which is just the chance that the ball, this is called a Rayleigh distribution also. This is a chance that the ball of radius r is empty of point. It has this density, right? Okay, so you recognize, you see, here the pi r2, which is the volume of the ball of radius r, multiplied by lambda, the intensity of base station, right? And then condition that, you know that the signal will be the power of transmission times r to the minus beta because of attenuation. And you know that the interference is that outside a ball of radius r. Okay, then you play this game and you see E minus lambda r2, and here you see the fade should be exceed this. And this if the fade is Rayleigh, this is nothing else as the Laplace transform of the interference multiplied by the whatever, right? R to the beta t blah. Okay. And the Laplace transform, and that's step 2. That's what I said. Since you have a Rayleigh fade, if you take a Rayleigh fade, this is do the simplest case, right? You can reduce that to the Laplace transform of the interference outside the ball of radius r at this point mu t r to the beta. That's the earlier formula. And there is a closed form for the Laplace transform of the interference of any point Poisson point. That's the interference short noise. You massage the two, and you get the formula. Right? For any fade, for the fade coming from. Okay, so it's as simple as that. What I want is to explain why this closed form. It's a little bit like in queuing theory, right? So you have the MM1 queue. Take everything Rayleigh, r to the minus beta, you get rho over 1 minus rho in the queuing theory, and you can do engineering, right? And so here, the same thing, and you can use that for design. And what you get, and why is it in a sense important? Because what you get are statistical average while taking the behavior of the other part of the system into account in a very large system. The other base stations do the same. They serve the user, right? And so there is some sort of reciprocity, and you really handle an infinite system where everybody behaves the same. And you can assess mathematically the spatial average seen from the typical user, right? That's it. And so there are lots of system-level questions. Really, it's a system-level analysis, like in statistical physics, where you take everything into account, including the reciprocity. The other base stations also serve their own guys, right? And you can start asking lots of beautiful questions. For instance, here is one that I will come back to. When does BS densification lead to a decrease of spatial efficiency? Think of the mean Shannon rate for the typical user. Can you densify forever? And what do you get? So if you take n is equal to 0, it's called the case where you, in a sense, neglect the thermal noise. So it's interference limited case. The formulas that I've shown So you remember what it was, right? This guy, there is no n. Look at what it is. Just integral of an exponential form, linear, right? With this non-constant. So you solve it in closed form, and you get an expression which is as simple as that. Rho was this function of t and beta, 1 over 1 plus rho of t and beta. Completely explicit form. And you see that in that case, this is scale invariant. And so our paper with Krishna and Jeff, we had this result that the property of cover is scale invariant, right? And it took us lots of time to understand that it was really very specifically linked to the power, to the fact that you take r to the minus beta with a singularity at 0, okay? The singularity at 0 means that it should be a far field, so in a sense it's not a good model for very dense thing, right? But r to the beta means that if you densify, your signal power will become very big because there will be a guy very close by, right? And this compensates exactly in the no thermal loss case the interference created by the densification of base stations. And this is scale invariant, okay? But we proved with Jeff and Ahmad, PhD student in Austin, that it's wrong. This is a far field thing. If you take any decent bounded above attenuation function and you densify, let nada go to infinity, then this property of coverage tends to 0. And we know roughly at what speed and okay. So densification becomes it's diminishing return as you densify too much, right? So okay, I'm done with the part I wanted to cover. There are lots of further points beyond Poisson. Poisson is marvelous, everybody knows. But it's, the Poisson is, well, for the good reason. It's like the MM1Q, right? You solve the simplest problem, get closed form, you're happy. You can complexify it as much as you want and do the MG1, the GM1, whatever. You can also get further propagation models. And that's what I said, you go beyond scale invariance. You can introduce obstacles for millimeter wave. I will describe that in the third part. BIMO, beamforming, and with Sanclay, we studied that with the Nokia Bell Labs colleagues lately. Power control, FDM, coexistence with Wi-Fi, successive interface cancellation, cramp, vehicular, whatever. So everything you can dream of, there is an incarnation as a stochastic geometry thing, and you can perhaps, if you are lucky, be able to solve and get, in some cases, at least integral forms, and in good cases, those. Okay, now I enter the core of the... any questions first, because I will elaborate on that. Any question? No. Okay, good. So now, stochastic geometry for 6G and beyond. So I will describe RIS and NTN, but there are lots of activities worldwide on deterministic networking, JCAS, ICAS, cell-free, and okay. So I mean, I think it's a relevant thing to develop this machinery to understand how these things will interact or interplay. That's the okay. And now I can introduce the topic. We go to RIS and health cellular network. Okay, it goes like this. So you recognize the structure we had with the base stations. They are Voronoi cells, the users, which are the dots there, right? The UEs. There is a typical UE, which is here. And then comes an extra thing, which are a cluster of RIS, which is associated with its base station. And so the sort of mental picture we had initially is this. Okay, you have the base station, you have, for instance, obstacles in millimeter wave. So this base station, there is a problem. For instance, there is a blockage to certain users. And the cloud of RISs around the base stations allows you to circumvent these problems by intelligent reflection. And so there is a base station, there is a street, there is a building, and you put the RIS there. This will be, in our setting, cheap things, right, which are almost passive, and you pre-tune the RIS to cover the street, which is not seen by the base station. So the idea is like that, right? So there are lots of variants, but so the key new thing here is the so-called matter cluster point process. It goes like this. You have a mother point process, which are the base station. Oh, okay, I don't know markers. Anyway, so I think the pictures will be right. Yeah, no need Cedric. No. Okay, this is a mother point, and around the mother point, you put a random shape. Here it will be an annulus, right? It could be a ball. And you put a daughter point process, which is Poisson with another intensity, which is the RIS objects, right? That you put in the, or you can do that close to a mother point of base stations, and you can put that around holes of coverage. There is, I don't know, some area which is badly covered because there is a hole or something like that. And you could put the RIS around that hole to cover the thing in such a way that the objects that do not see, the UEs that do not see the base station are covered thanks to the reflection by the RIS. Okay, there are plenty of variants. I will just describe the case where the mother point process is the base station and is a set of base stations with density Poisson with density lambda BS, and the RIS point process is a matter cluster point process in a ring around each, and there is a UE which form yet another Poisson point process and density lambda UE. Okay, and I think I already said it. The RIS cluster is meant to circumvent blockages from BS to UEs, and there will be a collaboration between several RISs in order to cover a given user. And these RISs are supposed to be informed to the UEs in a sort of very predefined. Okay, what is the main typical technical novelty? This is the fact that we had interference and signal. Signal was very simple. It was a single signal coming from the closest base station. No signal comes from the direct link, which may be blocked, perhaps, right? Use that in the model, and from the reflection of the UEs that beam formed to the user, those at least which see the user, right? And what is the small cloud of RISs beam forming to the user? It is a Poisson point process. Therefore, you can compute the power created by this Poisson point process and under OFDM assumptions and separation of distance, you can get a formula, an additive formula for the power received by the UE, which will come in two parts: the direct pass signal with power QSD, which will be handled using the Voronoi structure. I'll explain how. And the reflected pass, reflected by the RISs that being formed, and there will be an additive thing. Again, a shock noise created by a small Poisson point process, the Dr point process, with a power whose Laplace transform can be the miracle of Poisson is that you can compute the Laplace transform in closed form, right? Universally, and there is an expression for this power of the beamformed signal, right? Yep.
Donc, les hypothèses de départ, c'est que chaque station de base émet la même puissance, tout le monde est sur la même fréquence, yep. Et les RIS, ils se connaissent, et ils ont une fonction de transfert égale à 1.
Yes, so let me rephrase the question in Sanskrit. Okay. So the setting goes with omnidirectional base stations, right? Yeah. So because otherwise they would have to beam formed to the RISs, right? Yeah. So they are omnidirectional. The RISs, they know the streets that have to be covered. They are predefined so there are lots of elements, as you know, and you predefine a certain number of these elements, street by street, to be formed in these given directions, right? And a given UE may receive reflected information from the main signal and from a certain number of RISs. So the power of the base station will be 1 over mu, if you want. And the RISs are passive objects. They don't amplify. They are relays, and RISs are relays. They don't amplify before forwarding. They just reflect by phase changes in the phase of the thing with the small elements to be informed to that street, right? Yeah. And under sufficient difference, but the model incorporates it, under sufficient difference between the lengths of path, there is now a pass loss from the base station to the RIS, and another pass loss and another fade from the RIS to the UE. You message of that, and you get an expression for QSR and QSD.
And there is no relay fading between in these paths, like from.
We took Nakagami or RIS or things like that with the main thing and reflections, right?
Sorry to interrupt you.
No, these are good questions. And, Okay.
Do you assume anything about the orientations of the RISs?
Okay, good question. So, yes, so first, as you know, you have transmissive and reflective RISs, right? So in a sense, otherwise you would multiply the density of RISs for a given typical UZ, only consider those which have the right angle, right? So this is a good question. So this would be the subset of the density of RISs which have the right orientation, right? Okay, and the same thing, you know the interference power as well, characterized fully by its Laplace transform with a closed form, right? And therefore, if you ask, let's think of the SIR simply, ask exactly the same question, what is the chance SIR exceeds T? This is the chance, your first condition by where is the closest base station. So this will be the Rayleigh distribution for the empty ball condition of Poisson, right? And it's conditioned on that, this is the chance for the signal, direct signal, same thing, okay? You know any path loss function and the power. This guy will have some randomness, but it's a short noise, you can compute the Laplace transform. Over Qi, you can also Laplace transform exceeds T. You massage the thing, and it's a chance that QSD, which is the direct signal, for which, let's take again Rayleigh fade, although it's better to take Nakagami or RIS, right? Exceeds TQi minus QSR of I. QSR is reflected at distance R, right? And you see, if you take Rayleigh fade here, you have a certain random variable, an exponential random variable should exceed the difference of two random variables for which you know the Laplace. Okay, and so this is called the Wiener-Roch factorization problem. Actually, if this sign is negative, it's always okay. If this sign is positive, then you have to compute the law of that and to compare the variables. And there is in the Wiener-Roch theory an explicit integral form for the solution of this positive part problem. And that's what we solved with Bell Labs colleagues, I mean, Wodong, Luis Degas, and Stefano Paris. Kerfline was also part of it. Okay. And out of that, you can answer, so you get an integral form. So it's not a closed form. It's really complex, but it's an integral form, and there is we developed software to solve these integral forms using so it's numerical analysis, Gates Malik rule. But you can start, and that's what we do now, asking the influence of geometry and parameters. You have the density of RISs, the radius of the clusters, everything, right? On spectral efficiency, right? Is it better to have assume you have a certain number of elements, okay? The elements would be the cavity which you tune in order to make to change the phase, right? Is it better to organize them into many small RISs or bigger RISs in lesser number? And the answer is the second, right? So because the gain that you have been forming, so it's better to have fewer RISs with more for a reasonable range of parameters.
Sorry, what does it mean exactly? Physically, you are supposed to eliminate element by element?
No. The question is that, so you think of an optimization problem for reasonable parameters, right? And so you invest and you say the cost is the small cavities that you can tune.
Yeah.
And you can organize these elements, call them elements, which are the tunable cavities, which are based in the Matthias thing sense, right? Yeah. You have either a large number of small RISs with few elements or a smaller number of RISs with more elements.
But there is a basic element.
And out of
that you make RIS,
yes,
which is a group of small number of RIS basic elements or a large number of RIS.
Yes, and at constant cost, assuming that the cost is per element, fewer RISs with more elements are better. So that's what you say, bigger and lesser RISs. We have an answer for that, for reasonable, parameters which we also know, so we can compare, for instance, the situation where you cover holes. And so it's known already that the RISs should be put either close to the receiver, to the UE, or close to the base station, right? So intermediate is not good for reasons that are well understood, right? And we can assess that in function of the gain, function of the obstacle density, and the optimal arrangement, either the mother point processing base stations on whole. Right? So lots of these things we can do. And here is a curve which we got lately, which is, I told you, look at the red curve. This is the return on investment, right? This is the ergodic rate, the spectral efficiency, if you densify base stations. And I told you, if you take reasonable, maybe bounded above decreasing function for the path loss, right? There is a threshold out of which you invest base stations, and if your income is in terms of Shannon rate, well, it's not only diminishing return, it's negative return, right? Okay. Yes.
Sorry to interrupt you once again.
Please.
In the earlier analysis, you said that we have to take care of the fact that are we working in the far field or we are working in the near field? And just a few seconds before, you said that we have to take into account the risks which are close to the receiver or something like that. That gives you a better solution.
Mm-hmm.
So how do you match these two things? I mean, because when it is close to the receiver, then it is working in near field.
No. Here we always use far field, right?
Okay.
Always. But it is true, nevertheless, even if you restrict yourself to proximity, which is reasonably represented by far field, that it is better to have the cloud of receives either close to the transmitter or close, not too close, because you use the far field to the receiver, and not in the middle, right?
Okay.
There are half a dozen of papers which assess that, and very nice ones. And we understand why, because it's just, I mean, the multiplicativeness of path loss, so it's right. And so all these models are far field. And it would be very interesting to assess. I mean, if you want to assess real densification, you should in the end go to models which are near field, right? Which is not done. Okay, but so all these things are under a far field parametric in the parametric setting of far field. And as I said, we proved that with Jeff and Ahmad, that you get not only diminishing return, but negative return if you densify too much the base station. And these are on the ratio of cost of base station and RIS, what happens and when you should start investing in RISs. And the RISs, there is one thing I should have said. I think I said it. I said they are passive things, right? So they are pre-tuned in this model. They are pre-tuned, and the fades that they create to other guys, these are like relay fades, right? So, so in a sense, you have something in this model, which I think can be justified, where you really increase by beamforming the signal, but you don't alter the interference, because the interference is taken into account as a relay fade to the others, right? So there is a rare case where you would beamform in another base station to somebody who is in another cell, right? And this can be taken into account in the interference by having a main lobe and secondary lobe. Yeah.
When you speak about the rate here, you speak about the physical data rate of the typical user, or you take into account also the sharing, also in by packet. If you have a constant lambda for the UEs, you increase you densify the network. You share the capacity of the base station less users. So do you take into account this max output also?
Here we did what the two things are linked. So here because if you densify, it could be that some base stations are empty of. Okay, so you look at a typical time slot where you would do some time sharing, and the typical user, that's what this guy gets, right? And so, in a sense, under the assumption that there is at least one user in the cell. Yeah. So here you want to. Yeah. So here there are. sufficiently many users so that for whatever density there is at least 1%, and but the sharing, so you can ask further questions. You're completely right.
Do you consider the problem of the Doppler effect? I mean that when it comes to signal, when the receiver is far, there are multipaths, and the path has some meaning, and then it has an entropy and impact the capacity.
Yes, very good. It's a question. And so I assessed that. I said that we are using OFDM. And so the idea is that we assume that the multipath thing for the signaling from the various RISs, right? You can assess what the tap is, and the delay on these things. And knowing that, that's a reason for which you can, there is no like interference, destructive interference between two signals, right? So this is under this assumption. Otherwise,
then you have still.
Yes, but if you know this delay.
If you know the battery, which is a fast Doppler.
Yes,
it has an entropy, and maybe there's a easy way to get rid of it.
But so this is no. Currently, this is ongoing, and we look at this assumption where you can detect the tap, and therefore. Really, the power received is some of the power beamformed basis. Okay, thank you for all these questions. So let me say that in a sense, I mean, as we said, so here you can start answering. So there are plenty of variants, but you can start answering questions. We are economic questions, right? When is it timely? So there is no point. It is an optimal strategy depicted here. Before there is certain density of base stations, it's also useful to have RISs. If you densify the base stations only, you get the negative return. There is an optimal time in terms of the investment rounds to start investing in RISs. And depending on the ratio of cost between base stations and RISs, you can determine which is this branch point. So ideas like that are very natural, and this is what these things allow you to do. Okay, let me move to Zoom 2. So we'll be fast on that because I want to cover the third. Okay, so these are NTN based cellular networks. So this is a constellation. You see on the left a constellation of low orbit Earth orbit satellites. With you see the orbits. These orbital planes here have an inclination, like in the Starlink project or constellations. And the BS move on the orbit with an orbit having a given inclination. So it's completely new geometry. And there is a need. We started investigating on putting random geometry on orbits. What is a random orbit? What is the Voronoi cell when the base stations are in the sky? What is, can we get the coverage? Can we get the signal? Can we assess spectral efficiency and things like that? And these are system level questions because first, will be again, especially if satellites are in a row on the orbit, there will be a signal, but also interference. Even if there is beam forming, there will be secondary lobes, especially for very dense constellations. What is the interaction between? So, as you know, in 6G, this type of networks will interact with the terrestrial networks. There are lots of projects of using the millimeter waves of 5G within this setting in the the K and KU bands, and so what is the interaction between 5G terrestrial and NTN? What is the optimal orbit or satellite density? Further problems like 5G offloading analysis and things like that. So the whole thing was started by Niloufar Okatin in her PhD in Finland. And they have a very nice paper I strongly recommend, where they use, they forget about the orbits, and they display a so-called binomial point process. You have 100 satellites, or 1,000, so tens of thousands, and you put them uniformly located, independently displayed on the sphere, right? So on the altitude of like 350 or 400 kilometers from Earth. And so Niloufar, in her thesis, which I strongly recommend, studied exactly, she answered some of the earlier questions. What is SINR? And she says, let's forget about the orbits and look at that sort of parametric representation of the network with the density that matches what you would see locally if you would use Starlink, which is much more deterministic. So that's and as the orbit, right? And so it's a very strong paper, very interesting. Strongly recommended, right? And so what has to be done and is currently done is to introduce more geometry, namely orbit planes, and also, I mean, even if you take what we'll explain now, a Poisson point process on these orbits, you will have much more clustering than if you take independent points, right? So the clustering creates completely different things for interference and for coverage, right? So and it's very important to take that into account. That's what we do with the Stochastic choice in Seoul. So we built a stochastic geometry model with the requirements that we have orbital planes with a certain inclination. And the various longitudes, the ascending point I will describe a bit later. And we can address the distribution of LEO satellites, all these orbital planes, which creates a structure of interference, which has nothing to do with the initial models. Right? Okay, and the aim is always the same, right? So I perhaps pass on that. I just said it, right? And I want to explain a little bit about the technicalities, which are the first one. So what is a random orbit? You need okay. So it's a random. It's a plane, right? An orbital plane is a plane. Okay. And so you have to parameterize the plane. And so what people do in the Keplerian physics is that is the equator in gray, and you look at the inclination with respect to the equator of the orbital plane. It's a first angle, right? Omega. And then, no, omega, sorry, is the location of the satellite. So this pi, I think, it's an angle, which is the inclination of the plane. And there is the locus on the equator where this orbital plane, crosses the equator, right? It's called the ascend, and there are 2 points. You look at the one where the satellite goes up. It's called the ascending point, and you can parameterize an orbit and a point on the orbit with so the ascending point, which is an angle on 0 to pi. This angle, the inclination of the plane, plus the omega angle, which is where the guy stands on the 0 to pi for the whole circle. So that's. And you can define a point process on this manifold, and define a Poisson point process or a regular point process on that. And then, if you have that, actually it's called a Cox point process. You have, say, orbits and Poisson structures on these orbits. Then you can compute it, short noise in closed. So, but the geometry is spherical. There are lots of completely new things, right? So. And compared to the plane, there is a notion of visibility. Okay, so I won't describe too much, but there is a visibility cap, and you have to compute the length of an arc of a grand circle, which is an orbit on this orbital plane, and look at the points which are displayed there to compute the interference structure, right? And the law, and you can get the Laplace, and you can get in this structure the SINR in a rather explicit form. And answer the questions which I, in principle, right, which I say, so what is the SINR, what is the data rate, what is the impact of such a network on the terrestrial network, and things like that, it's at hand. Okay. Right, and as I said, I mean, you can guess what are the difficulties. You have to assess what the signal is. So what is the closest satellite? So you ask Voronoi on the sphere. You ask indeed Voronoi with this spherical geometry, which is completely new, and that will give you the power of signal. And the interference will be short noise by all satellites on these orbits except the closest. But in principle, this is the same machinery, right? So this is universal, right? So you can compute these Laplace things and get and hence get quality of coverage, spectral efficiency, and of course this will be for most deployment latitude defined characters. Okay, now I move to questions first.
The previous analysis assumption is that the base station is in the satellite, and the users are on ground.
Yes, this is downlink for the satellites, right? Luckily, it is very interesting. I did not discuss at all locally in time. But,
no, but I mean, we are trying to analyze the situation where what bit rate users will get, or what is the...
Yeah. Okay. The spectral efficiency, property of coverage, and it could be in some cases that you see no satellite, there is a visibility cap. So they're completely new concepts, right, that come from, which are very different from the terrestrial ones of, say, dance.
But then how do you take into account users in the, of different satellites, and once again, I assume that...
Closest. Yeah, that's what happens actually.
But now closest in
Euclidean geometry. Euclidean geometry.
Yeah. It changes a lot, you know, I mean, because the distance of elevation of the satellite and all these things.
Yeah. So Euclidean distance, right? So you look at the one, because I mean, you have pass loss there, which is very problem. It's why they put LEO satellites at low altitude, because that's where you get the pass loss, which is of course attenuation, which is compared to geostationary. So it's completely different. Okay, now RIS and NTN. Okay, so it's ongoing work, but okay. Oh, one thing I should say. Handover is a fantastic problem there, right? Because think of all these guys moving at Keplerian speeds, right? You get the closest, especially there is inter-satellite communication, and just thinking of routing and handover is an amazing. If you realize what it means, it's absolutely fantastic. Okay. Yes.
How about latency and delay systems?
Okay. Yes. Latency. It's linked to the presence of what are called anchor stations on ground. But if the satellite which serves you sees an anchor station, it's a few milliseconds, less than 10 milliseconds latency for LEO, because the satellites LEO, yeah, 300 and 400 kilometers. Do the calculation with speed of light, and so that's not the problem. It's but what is the problem is because you have is the handover frequency of handover. So it's completely.
And just in this situation, just consider the impact of signal from satellite. Then we have an integrated terrestrial and non-terrestrial network, in which we may user equipment, or maybe the base stations use the same frequency. Meaning receiving from terrestrial and non-terrestrial network at the same time. I don't know if you consider just limited remote.
We are handling this question in the sports archive paper with Namyunli, who was also a graduate student and now at the Professor Korea University. And so if you check this paper on archive, if you send me an email, I will give you. So there are very interesting questions. One of them is what is the impact of the non-terrestrial network on the terrestrial network if you use 5G. And that's what we answer here. And we have a sort of integrated model where we are both in the same geometric model, the terrestrial and the non-terrestrial. And we use the machinery to answer this question, which is a very simple question, should this thing fly one day? But there are lots of projects. There is a French company, Constellation Technology, which launches 2000 satellite constellation on millimeter wave band, and this will be each base station will be a few of these. So, I mean, people have this in mind. It's very. Does it answer your question? Please send me an email and I will point the same points. So, but these are central questions which are a little bit like those questions which were looked at in the past for cognitive radio. Like so, you introduce new features. But what's the impact of the thing that? Okay, so it's a new direction, but it's just to show you, I mean, the flexibility and the type of questions you can address in this new universe, right, of wireless stochastic geometry. And the question is, how much can reconfigurable RIS, right, augment sky visibility? Goes like this. Think of an urban environment. Think of millimeter wave, and so as I said, it's 6G will completely integrate what is currently done in this framework of NTN in the millimeter and perhaps even higher frequency bands used by these networks. Think of just the notion here. We will not want to do it, but we will not do it. We will not look at SINR or Shannon rate. We look at very simple things. So think of obstacles, buildings, block of view. You are in the street. There is a building here, a building there, right? And these buildings block your view. And so if you don't see any base station, and the only thing that would fly is to connection to a satellite, right? On this millimeter wave bands, which are right, because they are the same, right? But the thing is that there's blockage, right? So then think of RISs put on this building, for instance, close to the top. They will have a much better view, right? And just you want to assess again with this ensemble averages, this statistical physics viewpoint, what is the gain of putting RISs at the top of building for the piece of skies that you see? This is a very childish question, right? So the framework allows one to...
So the RIS will reflect the signal to the ground.
Yeah, yes, or backward, right? So
yeah.
This is the mental picture, and we are working it's a work with Junse also in South Korea. Junse Lee with the reference. That's you have the user here on the ground. And there are buildings, and so this would be again a simplistic view. So we can change that at will, right? And this building have length, height, and location, right? So these are segments, the random closed sets of the Euclidean plane. And think of a given direction. And what you see, I mean, there is the first building, second building, a third one, which blocks the view, and all those later you don't see, right? And assume you have put a RIS at the top of each building. We'll see what type of RIS later. It should be RISs which would be intelligent one, because they will have to follow the satellite. So this would not be a cheap things mentioned in the streets. And you define this angle, which is the blocking angle, right? Theta, which is the max of the theta 1, theta 2, and each theta is given as a function of x and h, right? H is the height, and x is the location of the building. Okay, so there is a 3D problem that we are spending a lot of time on with Junse, and a 2D problem which we have solved in a sense. And I'm a queuing theorist by training, perhaps some of you too. And so I name things here. It makes a lot of sense with queuing theory terms. There is the MM model where the buildings are homogeneous on R, intensity lambda, and the heights are exponential. With parameter mu, right? This is the MM model. There is the MD model. Guess what it is, right? Would we say Paris, right? All buildings are the same height except perhaps the Tour Montparnasse or something like that. So low. The DM model, more grid type things and things like that. And all extensions you can think of in terms of the queuing theory with the GG, GI, GI, blah. Okay. And right. And so let me explain again. So there is notion of short noise, and there is notion of max short noise. The max short noise is the operation where you replace the sum by the max. And there are closer expressions for the Laplace transform of the max short noise for Poisson point process. What do you have? A Poisson point process with expression marks. If you challenge me and tell me, François, get me the Laplace transform of theta, which is the max of this angle, it's a max short noise on this on this point process, right? With their marks, but that's it's not a problem. And there is a closed form for the this angle theta, blocking angle. It's a Frechet distribution in the MM case. It's amazing that when you put nothing in the system and you Frechet is heavy tail. I mean, it's a heavy tail. So perhaps you understand why it's heavy tail. If you just look at you look at the tangent of theta, of course, right? So the thing is that if you are close, I mean, this is Poisson things. So it's a little bit like what I was saying about the attenuation function being in r to the minus beta, right? If you are close to the interferer, you have a huge interference. If you are close to the wall, the angle is almost pi over 2, right? So you are near the feet of Tour Montparnasse, and okay. That's the reason. It's a Frechet distribution, and that comes from the analysis of the max short noise of this building point process, right? And this is this table, I mean, we have lots of results of this type when you, the shape parameter of this threshold is 1, and the scale parameter is rho, which is the overview, which is sort of the density of the urban system, right? So 1 over mu is the mean height of the buildings, which are exponential, and lambda, their intensity. And so first we thought it was too simple, right? And so we compare to 3GPP data. And so they have the parameters with the suburban, urban, and dense urban, right? Where you vary this rho. It's not in these terms, but we get a reasonable match, even a good match for this distribution, right? With this data from this. So we have plenty of closed form of this type for MD variable, which is used also in this one. Okay. Okay. Now think a bit more. We thought it very important to know the joint distribution or the joint density of the building achieving the blockage and its distance, right? So it's of the X plus and H plus, because this is where you will be informed to talk to the satellites later, right? So so does it make sense in terms of beamforming to something? Well, perhaps you see this tower very far away, but so far that beamforming there makes no sense, right? So you're just doing it, right? And so there is a closed form everywhere with lots of special functions. We like them. When we were young, we were playing with special functions a lot. And so the joint density has this closed form with the threshold part here, 1 over h. And you get the marginals. So the building blocking your view in the MM model is twice higher in mean than a typical building. The density of the building blocking your view is given by Baccelli functions. The second kind, and there are closed form expressions everywhere, right? So it's very fun. But no, actually, but but these things are important, right? Because the distribution of X in particular, of X plus H, the two are interesting, really tell you the feasibility of beamforming to the RIS there, right? And maybe not feasible, in which case you might have to go to amplification or several steps or multi-hop or things like that. Okay, now go to the center of this part, is the improvement on the brought by RIS on the visibility angle or on the visibility surface where the UAVs or the NTL can be found, right? So there are two types, we discussed it a bit earlier. The transmissive mode, where you can go the same direction, right? So it's at the top of the building, but you beamform to something that perhaps the user doesn't see through the UAV, which is here, right? And so here, what will be important is to assess theta is the blocking angle, theta for the transmitting mode at the blocking building. How much less theta t is with respect to theta, or if you take the complement side, how much bigger it is, right? Okay. And there is the reflective mode, which is also quite fascinating here, where you would beamform in a reflective way to a UAV, which is in the other direction with respect to the blocking building. Right? And so we studied these modes. And well, you can compute again everything, right? So this is an expression, I won't insist too much on the things, right? There are nice special functions everywhere. But this is the conditional CDF of tangent theta t. We are more interested in psi t, right? The complement, given that the blocking building is at X and H. And we know the distribution of that, right? And this is the expression for that. It's again a very simple closed forms. And you can uncondition that and look at the same for the reflective case as well. And okay. And so this would be now unconditioned, the sort of visibility enhancement. Get the CDF of that. That would be for rho is equal to 1. So here things depend on lambda and mu jointly. It's a bit more complex. But you get expressions for this improvement. You can find both angular metrics. So this is an angular metric. So you get the expectation of the angle at the top of this building, not the blocking angle, but the complement. divided by the expectation of the initial part of the sky that you see, right? And so this will be bigger than 1 always. Same thing for the reflection. And this would be the expectation of the ratio. And you get expressions for all these type of things. And this is what you get, right? So you see both the second metric, of course, is improvements which are way bigger. So that's all the sort of density of the urban system. And that's the how much more sky you see in angular terms if you put this receipt, right? So I mean, you see, these are quite substantial things, especially when you densify we look at linear metrics, which are, I think, perhaps more important. So since you have UAVs flying at altitude capital H, so you have this initial angle here, right? You have this initial angle. So you were seeing this part of this linear thing, right? And it could be that there is nobody there. And what matters is how much more you see when you see from the top of that building will be blocked by another building which is a bit more far apart. But you see an extension of the linear of the here line where it could be that UAVs stand or fly, right? Okay, again, for this 2D model, the MM transmissive mode, we have Clauson expressions for the length of the initial conditional on the altitude of the location and the height of the blocking building. You have Clauson expression for this. So L was the first length, and capital L was the new length, right? Get conditional means in closed form. And the interesting thing for this model, the expectation of capital L is infinite. So it means, I mean, just moving to this, and it's linked to the unconditioning, right? Moving to this building that blocks you, the gain in the linear span of sky visibility that you have in mean is infinite. Okay, so let me not describe too much this thing, but you get, for instance, lots of interesting expression using special functions in the polylogarithmic function showing up. For the probability that there is at least, you take UAVs which are so at this altitude on this line. Yeah, right? So phi u is the UAV point process. You look at the chance that the point process of UAVs at least a point in the long interval, thanks to the RIS extension of visibility, given at 0 initially. They are close form, and this is this chance as a function of these two parameters, altitude and density of UAVs. Nu. H nu, this product is here. And you see, I mean, conditional fact that you see nobody, if when the altitude is big, the chance to be covered, to have sky visibility. Covered will be another thing based on SNR. Really goes to 1 very fast. So I think you can make a case for economic decisions, right? Again, on the use of these things. Okay, so let me skip that. We are doing lots of things with Junsei on the 3D model, the multi-op case, refined statistics, signer coverage, and these are like 3 references. The RIS-SEG, this is a joint work with. It's published now. I'm sorry, I didn't put it. It was published in 2024 for the RIS case. The multi-altitude case we studied with Stochastic. It was published too this year, and the ongoing work with Junsei is just appeared in International Wireless Communication.
Long live India and France friendship.